So today we're going to discuss about derivatives. Most of the students from you already are familiar with the term derivatives or differentiation. And differentiation is just to find the rate of change of one variable with respect to another variable. And it is mathematically symbolized as this one ddx. ddx, d divided by dx, but it is not read as d by d divided by dx, it is ddx operator. ddx operator indicates actually rate of change. Rate of change of whatever variable or functions we write immediately after ddx. So it, after all, it gives us rate of change with respect to what? This x is here in denominator, x is here with respect to x. That means whatever function we write here, the function in terms of x, if it is in terms of x, then ddx represents rate of change of that function with respect to x. So ddx of suppose y, ddx of y, then it is simply we call dy dx. Y is what? Y is a function. In case of y, any function might be there: algebraic, trigonometric, logarithmic, a rational function, trigonometric function, inverse trigonometric function. Any function may be there in case of y. Y is equal to fx, we write fx also theoretically we can write here. So it is simply dy dx, read as dy dx, and its meaning is rate of change of y, rate of change of y with respect to x. How y is changing as x changes. If x is changing, how y will be changing? That result is given by this operator. So y is called dependent variable and x is called independent variable. And y is a function of x. It is dy dx means differentiation of y with respect to x, or derivative of y with respect to x. In case of y, any function may be there. Then derivative of that function with respect to x. Now that function actually in terms of x, that is function of x. Whatever in case of y is there, that is just anticipated here in this case, functions of x. Suppose y is equal to sin x, y is equal to cos x, y is equal to x square plus bx plus c. Any function may be there in case of y. So change of rate of change of that function with respect to x is indicated by this operator. So, so many aspects are there. Basically, there is some, there is a particular definition in terms of limit. Using that definition, we can differentiate functions, which is very lengthy, laborious, and to cut short that one, some formulas are there. Using directly formulas, we can compute, we can uh, find derivative or differentiation of functions with respect to the variable concerned. So that definition, using the definition, which is concept of limit, is also there. So that aspect is not considered here in our discussion. Just using formula, how we can differentiate a function with respect to its independent variable. That is that will be discussed here in your portion, differential calculus it is. And after that, fundamental concept of integral calculus will be there. So it is a huge part actually, but simply computation part using formula. How using formula we can differentiate function, that will be discussed. So here, so many formulas are there. In the part one, just few formulas considered to discuss. Here in the first part, these formulas are here, which are very much essential to remember. You know the first formula, ddx of k. K means any constant, 2, 3, 5, 6, a, b, c, any constant that is not x. The denominator is x is here. This x means a variable, independent variable. And this is k. K means any constant. A constant means not x simply. Constant means not x. If any constant is there and we are going to differentiate the constant, the result is always 0 because it is constant. Constant means constant, no change occurs. So that's why change of the constant is equal to 0. In that sense, its result is 0. And ddx of x to the power n. ddx of x to the power n is equal to, we can write the result, its differentiation result is n into x to the power n minus 1. Very fundamental, widely useful basic formula of differentiation, x to the power n. N means any number. It may be positive, it may be negative, it may be fraction, it may be rational, it may be irrational, whatever it is. N is any real number. Then we can apply this formula. X to the power n. Structure of the function simply x to the power something. X in the base and n in the exponent. If n to the power x, that you cannot go through this formula. If the function is of this form exactly, x to the power 2, x to the power 7, x to the power anything, then you can apply this formula ddx of x to the power n. And result will be written as like this. Whatever n is there, n into x to the power n minus 1. Very fundamental and basic and widely useful formula. And ddx of e to the power x. E to the power x is exponential function, you know, its differentiation remains as it is. ddx of log x with base e, its derivative is 1 by x, and ddx of a to the power x. It is a to the power x, not x to the power something. It is a to the power x. It is quite different with number 2. In 2 it was x to the power n, variable to the power constant. And here in 5, constant to the power variable. Then its result is a to the power x log of a. Um, in the first part, just these formulas are considered here. So let's take few examples. Very simple way we are going to discuss the formula number 2, how to apply the formula 2. Formula 1 is simply derivative of constant, always 0. It will be used directly in the numericals. And this is the formula which we can apply in different examples. So example 1, you see ddx of x to the power 5. So ddx of x to the power 5, it is, the function is x to the power 5. So out of this formula, definitely this is of the form x to the power, and that is formula number 2. So as per this formula, we need to write n into x to the power n minus 1. And in the same way, it is written the result. You see here, n is equal to 5, x to the power n type. So n is 5. So according to this formula, we need to write n into x to the power n minus 1. N means 5. So just in place of n, 5 is written. N into x to the power n minus 1. 5 minus 1 means 4. So 5 into x to the power 4, this is the result. So 5 into x to the power 4 is the result of differentiation x to the power 5. Similarly, another example, ddx of 1 by x to the power 3. It is 1 by x to the power 3. It is initially, it is not exactly same with formula number 2. But if we make an adjustment, very minor adjustment, then you see ddx of x to the power 1 by x to the power 3 means we can write ddx of x to the power minus 3. So 1 by x to the power 3 we can write x to the power minus 3. So now it is, you see, now it is of the form exactly formula number 2. So we can go through formula number 2. And as per the formula, same thing, n into x to the power n minus 1. N means here minus 3, not only 3, minus 3. So n means this, so minus 3 into x to the power n minus 1. Minus 1 is in the formula, n minus 1. So n minus 1. Just n is replaced by minus 3. And the result we got minus 3 into x to the power minus 4. Minus 3 minus 1 means minus 4. So x to the power minus 4. And next example is the ddx of root over x. ddx of root over x. Again, this function root over x, it is not at the uh, first sight you cannot compare this one, that this is we cannot go through any formula of from this set, uh, because it is different in looking. So it is root over x, but root over x can be written as x to the power half. When it is x to the power half, then automatically it will indicate the formula number 2, x to the power n type. N means any number, any real number. So x to the power half, now it is x to the power n formula. So according to the formula, we can get a result n into means half into x to the power n minus 1 in the formula n minus 1. So half minus 1. So half minus 1 means minus half. So x to the power minus half. Actually, this is the result, half into x to the power minus half. But x to the power minus half means x to the power minus half means 1 by root x. So just it is written in simplest form, 1 by 2 root x. 2 already there, and x to the power minus half means 1 by root x. So it is just expressed as the simplest form, 1 by 2 root x. And in another example, 5, the dx of ddx of 1 by cube root of x. Again, the form of the function is 1 by cube root of x. It is not at the first sight that not to the power n, but just this function initially, then we have x to the power minus 1 by 3. Exactly, cube root of x means x to the power 1 by 3. Again, it is in the denominator, so x to the power minus 1 by 3. Minus sign will be coming here because of line in the denominator. Now it is formula number 2. It is of the form x to the power n. N means minus 1 by 3. So according to that formula number 2, you can write the result directly. Minus 1 by 3 into x to the power minus 1 by 3 minus 1. And so we got this 1 minus 1 by 3 into x to the power minus 4 by 3. And next, you will look at example number 6. The dx of cube root of x square. Again, cube root of x square can be adjusted as this x to the power 2 by 3. And it's 10 minutes in hand. So x to the power 2 by 3. Now it is again x to the power n form. So as per that same formula, formula number 2, you can write the result directly, n into x to the power n minus 1. And by doing this, we got 2 by 3 x to the power minus 1 by 3. So these are the ways how we can get the results of differentiation using formula 2, and which is very much essential and widely useful, and very basic also it is. So that's why based on this formula number 2, I'm giving you examples here, and from your side you can you can pick up any examples, any basic numericals based on this formula from any books, any scripts, or any uh, websites. So main thing is you must remember the formula. So it's huge formula list. There is a huge formula list, and as per that list, so many formulas I'm not giving today all together, but part-wise I am giving this. In the first part, is three formulas given, and based on these three formulas, you can go ahead to some basic examples. And properties, two fundamental properties are there related to basic operations. There you see if any constant is multiplied with any function as a whole, dx of k into fx, k is any constant, then you can write the constant outside the operator and we get k into dx of fx. Simply the constant is considered outside the operator and then it is ready to represent the function. Example given, ddx of suppose ax square, a is constant. A is constant. Why it is constant? Because it is after all not x. So it is not x. So that's why constant. So constant is written outside the operator. Now it's left ddx of simply x square. And we can go ahead using the formula. So thus, if constant is multiplied with any function as a whole, then constant can be written outside the operator, and then we can uh, go ahead using the formulas. So next, party number 2, DTX differentiation of any one function, I mean two functions or more than two functions, if they are in addition or subtraction form, then we can differentiate function term-wise. Fx is one function, gx is another function. There may be another hx function, px function. So it is not it's showing here only for two, but more than two functions might be added or subtracted here. So term-wise or function-wise, we can differentiate. So whatever sign is there, it will be um, carried out accordingly. So ddx of the first, if it is plus then plus, if it is minus then minus, ddx of the second. So ddx of the first function, differences of the first function, plus or minus differences of the second function. Very simple property. Whatever terms are there and whatever functions are there, just term wise or function wise, you can go ahead using the differentiation. Very simple example I am giving here how to write this. ddx of these two. Suppose x square plus x cube is one function and this is another function, and the two terms are there. We can differentiate it first. Here plus, so it is plus. Then differentiation of the second, so derivative of the second. So these two are fundamental properties. To be familiar with these properties for you to do some basic examples, basic numericals on differentiation. So as it is the first class, we have discussed this much, just how to operate uh, the differential operator and how we can use formula to compute derivatives of some given function. So that's all for today. Thank you so much.
Thank you, sir.